Okay, so in this video we'll do a couple of examples where we use a substitution in a smart way in order to simplify an integral with trigonometric functions. And let's look at this integral, for instance. It's the integral of sine squared times cosine cubed of x dx. And we know about sine and cosine that, well, the derivative of sine is cosine, right? And the derivative of cosine is minus sine. And so if one were to try using one of these as your substitution rule, you would try to find either a lone cosine term or a lone minus sine term. Stick it together with your dx, form your du. And if you look at the terms that we have here, right? The sine squared, that's an even power. Cosine cubed, that's an odd power. And we'll see in a bit how this plays into picking which substitution you want to use. For now though, let's try both substitutions. All right, so first, let's try making the substitution u equals cosine x. Right? I mean, we only really have like two options here that are obvious, sine or cosine. So let's try cosine. This gives us du equals minus sine x dx. And what happens here is I can rewrite my integral in the following manner. Right, so I need this minus sine x term to appear together with the dx at the end here. Okay, so what's left? I'm left with a negative sine x and a cosine cubed. Right, so the original integral is now equal to, so I'll call that I, it's now equal to this integral. And remember, when we're making a substitution, what we want is to write everything inside your integral in terms of whatever substitution rule you're choosing, which is cosine x. And we're fine with the second factor here, right? That's u cubed. And this term inside the parenthesis, minus sine x dx, that's simply du, right? Again, because of the substitution rule. But how about minus sine x? Well, you're not going to get something simple here, right? If u equals cosine x, then sine x is, well, you can use the identity sine squared x plus, well, in this case, u squared is equal to 1. Right? And solve this for sine x. And you get an expression involving u. So that's not really a nice way of doing it. And as you'll see, when I perform the other type of substitution, u equals sine x, this will actually work better. Du equals cosine x dx here, and my integral is equal to, okay, what do I have to do here? I have to isolate a cosine term, stick it together with my dx, and what I'll have left is sine squared x cosine squared x. And now I want to rewrite everything inside here, aside from the du term, simply in terms of sine x. And that's easier to do in this case, because using the same identity here, sine squared plus cos squared equals 1, well, cosine squared can now be written as 1 minus sine squared x. And therefore, now we can make my substitution, u equals sine x, to get u squared 1 minus u squared du. And this is now a really easy integral to evaluate. Right? That's just a polynomial in u. And so you integrate and then you substitute your sine x back and you get your family of antiderivatives. But to just speak about this problem in a more general manner here, if you consider what happened, the issue with the first method was that we ended up with an odd power of sine. Whereas in the second method, we ended up with an even power of cosine after you isolated one copy of it. And this is what we want. Right? We want cosine squared instead of just cosine, because your trigonometric identities are written in terms of squared terms. So when I see a sine squared anywhere in my integral, I can replace that with a 1 minus cosine squared without having to deal with, say, square roots. And so this tells me that if I have an integral where it's in the form of sine to a power, cosine to another power, then what I just really need to do is to look at which power is the odd power. If m is odd, then that means I'm going to use u equals cosine x as my substitution. Right? Again, the reason is having an odd power for sine means I can safely isolate a copy of sine with the dx and have an even power left. So I can express the rest as 1 minus u squared, or a function of 1 minus u squared. Similarly, if m is even, if n is odd, that's the other term, if n, the power of cosine, is odd, then I make u equals sine x by substitution, right? Because now I'll have an extra cosine term to stick together with the dx. And, well, now you may be wondering, what happens if both powers are even? Right, so in the previous slide I said, if the power of sine is odd, you use cosine as your substitution. If the power of cosine is odd, then it's u equals sine. So it turns out if both of them are even, then making the substitution either u equals sine or u equals cosine, you'll always run into that case where you'll have an integral with a square root of something. And, well, again, we don't really like that, right? It becomes a bit harder to evaluate, when in fact there are other easier methods in order to simplify even powers of sine and cosine. In fact, you probably remember these trig identities. Sine squared is 1 minus cosine 2x over 2. Cosine squared is 1 plus cosine 2x over 2. And, okay, so how does that actually help us here? Let's see. This is equal to, okay, so for sine x squared, or sine squared x, it's 1 minus cos 2x over 2. Cosine to the fourth power, so that's cosine squared squared. So I have two copies of this. I'm just going to write it all out, so you see what's happening here. Right, so this was my sine squared. This was a cosine squared, and this was a cosine squared in the original integral. Okay, what's next? Okay, I'll isolate the 8 first from the denominators. And, well, okay, if I multiply the first two terms, that's just a minus b times a plus b. So this becomes 1 squared, which is 1, minus cosine squared 2x. Right, and on the right I have 1 plus cosine 2x still there. Okay, so can you think of a way to evaluate this? What's 1 minus cosine squared? Again, that's sine squared, using our basic trig identity. And so now we have sine squared 2x times 1, right, distributing sine 2x squared into this term, plus sine squared of 2x times cosine 2x. And now you can actually split this integral up into two separate integrals. Right, so calling them integral 1 and 2, let's just ignore the 1 over 8 for now. The integral of sine squared 2x, again, that's still just power of sine, power of cosine, where they're both even, right? Sine to the second power, cosine to the 0th power. Again, you don't have an odd power, so you can't use, or it's not advisable to use, sine or cosine as your substitution. Well, again, just use this, right? It's your half-angle formula. So now if it's a 2x inside, on the right side it becomes a 4x. right? The angle inside the argument doubles every time you use this formula to get rid of a squared term. And this is not easy to evaluate, right? It's just 1/2 x minus sine 4x over 8. Okay. How about the second integral? Sine squared of 2x times cosine of 2x dx. Well, now we can make a substitution, right? Cosine has the odd power. It's cosine to the first power, which means we make the opposite term, your substitution rule, sine 2x, giving you du equals 2 cos 2x. Right, so I need a 2, and I need to divide by 2, right? So 2 cos 2x, divide by 2. And I'm going to end up with 1/2 u squared du. Again, really simple to evaluate now. And just combine this, and you get your final answer to this integral.